Oh.
You start the video and everyone goes home.
Yeah, exactly. That's not going to sound right the first 5 seconds of the video.
I made the worst sounding.
Anyway, so that's it. That's where we've got on probability. These are the probabilities coming up, binomials, and sampling. This is what we'll hit. And then the next page, we'll get into the last 4 chapters of the book. So if you flip your formula sheet over, this stuff is really the second half of the book. That stuff is the stuff we've been flirting with all year. That stuff is the stuff that I said, hey, make sure you're solid on standard deviation. Make sure you're solid on that empirical rule, 66.599 or 68.95.99. Make sure you're okay with that because it's going to show up again and again and again and again. Notice we're using standard deviations, standard deviations, standard deviations. They're all over the place. Okay? And the rest of the formulas, that's all the formulas they're going to give you. The rest of the stuff is actually tables. And you guys have already covered, in this class we've covered that first table, which is your normal distribution table, and z-scores. And z-scores are going to show up again in Chapter 7 and Chapter 8. We're in Chapter 6 right now. So we're going to go back to z-scoring stuff. And hopefully, if I've done my job right at Chapter 7 and 8, is when you'll see Chapters 3, Chapters 4, Chapters 1 and 2 coming together with the rest of the statistics we've been doing. You saw a little bit of that with Chapter 5 with the linear regression, hopefully. Okay? All right, that's it for the formula sheet. Those are the formulas we've covered up to this point. I just wanted to remind you of that and be cognizant of that because we're going to continue to cover those things. Conditional probability, that's the probability of E given F. Yesterday, we worked kind of like a fair amount of these, just working through, plugging into the formula and getting our probabilities. What I want to do now is where we ended the day yesterday with this data set, conditional probabilities. I think we got started on the topic of car insurance for a lot of you guys. Is that right, with deductibles? And hopefully, I mean, even though it wasn't directly on the slide here, you got a little bit of understanding about how statistics actually does come into play in businesses like car insurance and in businesses like actually insurance all the way overall. Okay. Well, one of the other things you can buy, has any of you guys played the game of life? Anybody spin the wheel, right? How many people have played that game of life? Okay. When you play the game of life, you guys know you guys get those options to buy insurance or not, right? Life insurance, auto insurance, and all that kind of stuff. Here's the deal. Not only can you buy, well, you're required by the state of California to buy your auto insurance if you're going to drive a car. And if you're going to own a home, you're required to buy homeowners insurance. However, the other insurances are optional. Life insurance is one of those things that is optional. But it's kind of a cool deal. And it's not kind of a cool deal. And here's how it works. You're worth more money dead than you are alive. And here's what I mean by that. As an adult, if you have a job and you have kids and you want to make sure that your kids have money should you decease, which is an issue as a parent, and your parents, many of you guys probably, parents have life insurance. And it's insurance to say, if all is good and well, then your parents should live to old age. Right? That's what we expect to happen. In fact, statistically speaking, insurances have life tables. And people get paid very good money to predict how old the average person is going to live. If you live in California, they can predict pretty accurately on average how old somebody's going to live. Based on your genetic background, they can predict how old you're going to live. Whether you're male or female, they can predict how old you're going to live pretty well. Bless you. How many people, this is kind of tangential here, how many people have heard of Social Security? Okay. Just to kind of clue you in on what Social Security is, it's something that when you work and get your paycheck, you guys have already heard, some of you guys actually know it firsthand, some of you guys have probably heard from your friends. hey, when you get a real paycheck, not when you're babysitting, it's going to be a great video today. Not when you're babysitting or mowing the yard and getting paid cash, but when you actually have a job that you get a paycheck for. How many people have gotten a real paycheck from a job before? What's the first thing you notice when you got that real paycheck with that real job? Deductions. Didn't that really make you angry the first time you see that happen? Okay, if you haven't seen it happen, you'll get your paycheck. It'll tell you how much money you actually earned, and that's going to be a big number at the top of that check. And then you're going to look to see how much amount you actually got paid. Those two numbers are not the same. Okay? They take out taxes, and then they take out this thing called Social Security. Now, Social Security is something that they do. It says this. Everybody can retire at age, whatever, 65. And what happens is if you paid into Social Security, what the government's going to do for you is they're going to take a little bit out of every paycheck you earn, and they're going to invest it for you. And hopefully if you guys remember something from, say, Algebra 2, there's this thing called exponential growth. And if you look at money and you compound your interest, it will grow exponentially. And I think you guys would agree, it'd be great to grow your money exponentially. Maybe you'll agree with that. The catch is if you're going to grow your money exponentially, you need two things. You need a good interest rate and you need to have time. So what they do is the United States says, hey, I can't remember when Social Security came into play. Way more than that. It's 50s, 40s, or 30s. It might have been the 30s. Is it 30s? Okay. So you're looking at Social Security. This system came in place right around probably Great Depression, FDR type stuff. And they said, we're going to start pulling this money out, and we're going to invest it for you so that when you retire, we're going to grow it exponentially for you, and then you can retire on that. And that was based on this. Lots of people putting in and growing that money so that it grows for 30 years or 40 years, and then people start dipping out of that money when they retire. And it should make sense that when people retire, we've got other people starting their careers here, so they're going to continue to put in money to refund. Refund not means to get back, but to put money back into that fund. Okay? So that means when people retire, we still have people putting in, so that money is going to be the same kind of growth over time. And that's a great idea, and it works. Now the catch is, when we started in the 30s, people only lived to about, I don't know what life expectancy. I'm going to make this up just to illustrate a point. I don't know the fact for sure. We'll say the life tables were 68 years. In the 30s, it probably was less than that. Anybody have a rough idea? Anybody remember life expectancy in the 30s? I'm guessing it was less than that. I don't know.
Pretty close.
Pretty close? Okay. Okay. So we're going to call it in the 30s, life expectancy was 68. That means the people who run the statistics, and they were correct at the time, that if they retire at age 62, you're only going to have to pay them for how many years on average? 6. So if they put in for 40 years of their career, but I only have to pay for their retirement for how many years? Is this exponential growth going to keep growing and growing and growing? It's true. This would, but aren't some people going to live past 68? Yeah. But if people live past 68, we're going to have people that what? Die before 68. We're going to have people that die over here at 50, and then I don't have to pay that Social Security. Does that make sense? So, this is going to be normally distributed around that age 68. And we should understand what that normal distribution is in terms of life tables. So, this idea of Social Security with money growing, people taking out, people putting in, it's a solid idea. Now, here's what happens in the 50s, 60s, 70s. In the 50s, 60s, and 70s, when you guys exited World War II, how many people AP US and regular US? Because you guys have to take regular US too, is that right? It's either AP US or regular US? So you should have talked about the baby boom, right? 50s, 60s. So what happened? Baby boom, World War II ends. We've got now a ton of people joining the workforce. All those baby boomers are in the workforce. All of a sudden, this Social Security, now we've got tons and tons of people putting in over here. Government's saying, and people are saying, hey, this is sweet. We're going to have these baby boomers work for 40 years. Everybody's put into Social Security. They're going to retire. We got this whole thing funded. It's a good deal. Now, here's what happens. That baby boomer generation, it sounds like you guys know what I'm talking when I say baby boomer. A lot of people the same age. That's key for baby boomers. All the men came back from World War II. Everybody had babies. That means all those babies are the same age. That means you join the workforce at the same time, and it also means you do what at the same time? Retire. Easy, pessimist. It means they all retire at the same age. And also, Andrew, they all die at the same age. Here's the catch. Retiring at the same age, the baby boomer generation retires at the same age. Life tables and life expectancy from back when they started this statistical model to now, because the baby boomer generation is retiring right about now, is the life tables are now up to like 72-ish. Do you see a flaw when this was the expected retirement plan and this is what life expectancy is? Okay? That's a big flaw number one. You guys should see the statistical relevancy, if I can say that word, the statistical relevancy of a life table increasing and not changing this age to retirement. Plus, the other flaw in this system. The government said, hey, we got baby boomers putting into this thing. This is great. We've overfunded Social Security. So the government says we can borrow from it. So the government borrowed from Social Security. It's the same thing. Social Security is tax dollars taken away, isn't it? It's just on two different. If you look at your paycheck, it's two different items. One says federal tax, the other one says Social Security, and the other one says like state tax. And your state tax is really small. So if you guys actually look at your paychecks, you're going to see those three things taken out. They're all going, remember, Social Security and federal tax is going to the same government, and they're just sorting the money out there. But then the federal government has borrowed from Social Security, and they allowed some people to take from Social Security that didn't pay into Social Security. Flaws in the system. So when you guys hear, hey, Social Security has some issues right now, that idea of growing money over time, sound. The idea of everybody putting into it and pulling out of it is a sound idea. Flaws. Life tables, people living longer. Taking out of it and not putting it back in. You should see now, hopefully, when you hear the conversation, Social Security has issues. And some of your parents or some of your grandparents may be dealing with these issues right now with Social Security. They're not getting as much money back from Social Security as they were supposed to get. Or the federal government has said this. You know what? You're allowed to retire at age 60 or age 62. But for every year you continue to work and put into Social Security, I will pay you a little bit more after that. For example, you can retire at 60 if you want. If you retire at 60, I'm only going to give you $1,000 a month. I'm just making this number up as a round figure. But if you retire at 62, you work 2 more years, I'll give you $2,000 a month. Does that make sense? It's all statistically based. They know that they can still grow that money for 2 more years, and they will have to pay them less 2 more years at the back end from an expected value. You see what I'm saying? All I'm trying to do is paint for you guys the real-life application of where these statistics that, yes, we're basically doing this stuff. And this is Stats 101. This is intro. But I want to tell you, there's people who are a lot smarter than me, who make a lot more money than I do, that really understand what's happening here to make those judgments that you guys see on a daily basis. The reason you get taxed the percent you get taxed, the reason this happens the way it happens, is all based on mathematics. However, some of their logistics is flawed. We know, I think you guys will know right now, if I borrow more money, how many of you guys have your own savings accounts, checking accounts? When you get to 0, can you take any more money out of that? No. Nope. But the flaw here is you can just keep taking money. Federal government can print more money. Now, for those of you guys, how many of you guys are in econ right now? You're in econ right now. You guys talking about inflation?
Talk about that in U.S. history.
U.S. history. the federal government can always print more money, but the problem is if you just print more money, what happens?
The value of the dollar goes down.
Yeah, not so good. All right, there you go. At least a little glimpse of you.
But wasn't the retirement age 56?
Could have been, like I said. It may have gone 56 to, it is always adjusted. And I want to think maybe, and I don't know, maybe 20 years ago, it may have been 55.
No, I'm saying the current retirement age, because my dad just turned 56 last year and his friend retired.
That's it. You can retire whenever you want. I think 55 is the minimum age to withdraw from Social Security.
Okay.
I think, and I'm not positive, but my wife and I's goal is certainly to retire before 55. Now, here's the deal about teachers. Cool thing about teachers and the bad thing about teachers. I don't put into Social Security, but I can't pull out of Social Security. But I pull in if you look at my paycheck, I get deductions for my own retirement account, and they are going to grow my money for me that way. Does that make sense? So my retirement is funded. It's just not funded through Social Security. So as a math teacher, I'm like, well, Social Security I don't really care about because it's not affecting my retirement. That's actually flawed. But I do believe 55 is the minimum age in order to pull. If you put in, that's the minimum age to pull from. But they're going to incentivize it in such a way that says, hey, 55 is your option. If you hold off till 60, it's worth an extra $500 more per month for it. You hold off to 65, that's an extra $1,000 more per month. And you're talking at that point, I don't know, it depends on how long you put in. It's all based on how much you've put in. So if he's put in for 40 years, he could be getting a check for $3,000 a month, $3,000 to $3,500 for another 3 years of working. Is that worth it for you? And that's what people have to now make their own personal choices. Would I rather be retired for 3 years at $3,000, or would I rather work 3 more years and get $3,500? Okay. Meanwhile, back at the insurance stuff. These guys. What is the probability that you have, and I think we covered this yesterday, a medium auto deductible given that you have a high homeowner's deductible? The catch in this problem, it's the same formula. How many people already run this problem? Anybody have an answer yet? A couple of you guys? This is a conditional probability of medium auto and high homeowners will be the probability of them both divided by the probability of high homeowners. And once you've got the formula there, you should be able to say, or we should be able to figure out this probability and calculate it. First off, I tend to think students like that. The intersection is easier to find. We're looking for the intersection of medium auto and high homeowners. Medium auto and high homeowners, that intersection is 10. It's 10%. The probability that anybody in this chart has both medium auto deductible and high homeowners deductible is 10%. By the way, if I were to sum all those percents up, what had they better sum to? 1. Does that idea make sense for you? Should. Not 100. I want to bank with you if that's good. Divided by the probability of high homeowners. Where is the probability that somebody in this group has high homeowners? It's a whole column here. Does this person have high homeowners?
Yes.
Does this one?
Yes.
Does this one?
Yes.
Notice that this is an or situation I talked about yesterday. You could be here, or you could be here, or you could be here. But you can't be both here and here. That make sense? So high homeowners is going to be 0.03 plus 0.1 plus 0.15, which is actually going to be that total down there. What is it, 0.28? Is that right?
Mm-hmm.
So our probability that they have medium auto insurance, if, it's another way to read that, if they have high homeowners, it's going to be 0.1 divided by 0.28. I don't know what that is. 0.357 sounds right. Do we see how that formula matches up? And do we understand what that probability is giving us? All right, next up. Probability no homeowners deductible, given that you have low auto deductible. Some of you guys are starting to see that patterning right now. Up top is going to be no homeowners. and low auto divided by low auto. No homeowners and low auto. Low auto and no homeowners. So that should be 0.04 up top. Divided by the probability that they have low auto. Where is low auto insurance now? Hopefully you're thinking it's here, 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 and here. You've got to add all those up together. I think it comes to be 0.18. Somebody might want to check me on that. So to get that probability, it's 0.04 divided by 0.18. And that should come out to be 0.22. All right. Do we see the process? I want you guys to do this one. This is the hard one. We're going to solve this. Given that the individual does not have high auto, what's the probability that he or she does not have high homeowners? I'm going to write it down. Probability, high homeowners, and I'm going to write C, which is not. Are you guys okay with that for the complement? So it's not high homeowners. Given, well, this is just helping me come up with my equation, which I think is the biggest issue for you guys. Because I know you guys can put the two decimals in your calculator and tell me the new probability. It's figuring out what to put in the right place. So it says, what's the probability here? She does not have high homeowners. So I say high homeowners complement, which to me I read as not high homeowners. And given, what do they give me? They don't have high auto. So I'm going to say high auto not, or high auto complement. Yo.
So you have to start with the bottom one first?
In the way that this problem is written, you need to identify what is given. It's not always going to be formulaic like this was. Notice that I've been giving you kind of spelling it out here. Where we're going is that I'm going to give you a probability. Sometimes the given will come first, like in this case. Big clues are the words if and given. Those tell you it's a conditional probability. Sometimes the if comes at the beginning, sometimes the given comes at the beginning. That'd be a lot more formulaic if it says, what is the probability that he or she does not have high homeowners if that individual does not have high auto? You can read that as a condition. Sometimes it'll say, what is the probability that he or she does not have high homeowners given that they don't? Read it and realize they're all asking the same thing. Look at the structure. Given is the condition, if is the condition there. So, some groups had numerators correct, some groups had denominators correct, some both have both correct. The first thing that I'm going to look at is this. My formula needs to be the probability of not high homeowners and not high auto divided by not high auto. Okay? Does that kind of fit with translating from wordies to statties? Yeah? So let's take care of my denominator first. Probability of not high auto. Not high auto. Well, here is everybody that has high auto insurance. Do we agree with that? That's everybody that has high auto insurance. So, isn't this everybody that does not have high auto?
How do you determine like which one goes first, like the high homeowners or high auto, like in the thingy? So then you can see which one goes on bottom. Because I switched it and I put in high homeowners on bottom. I'm sorry.
Anybody tune in last 5-10 minutes?
No. Your given always goes second in the equation, and then the second one is divided.
Okay.
The given, the key word you're looking for in the problems is given and if. Given may sometimes come at the beginning. If may sometimes come at the beginning. The condition when looking at the formula, must always come second. In fact, this line statistically means given, or that's your condition, or if. So that part has to come second. That part will always be your denominator. It's also, in terms of the bucket, it's always going to be bigger than your numerator. Think about how fractions work. We're looking at probability. It has to be a smaller number on top of a bigger number. Otherwise, we're going to end up with a number bigger than 1. That won't work. Are we okay with this probability down here for being not high auto? I think that comes out to be, what, 0.65? Is that right?
Yes.
Now, we need both not high auto and not high homeowners. Well, this is high homeowners here, isn't it? Not high auto and not high homeowners is everything that's left in this box here. And that represents that intersection. And I don't know what that comes out to be. What was it? 0.52? 0.52 divided by 0.65 comes out to be 0.8. Okay? That's a pretty difficult conditional probability. But I want to make sure that you're okay with A, my studies there. Is everybody okay with how I wrote it? And everybody okay with how I calculated it? What's up? Not bad. I don't think. They're not bad. Different. They're going to be different. They're not going to all be conditional. But as far as level, they're probably there. All right, here we go. This question I want to pose to you guys right now. We're looking at all the families that have 2 kids. All the families that have 2 kids. And for all intents and purposes, we're going to say that it's equally likely to get a boy or a girl. And if you look at the whole world, I think the percentages are like 0.49 something 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 and 0.50 something something something. So it's really close to 50-50. So we're saying 50-50 male or female. There's 4 possibilities right now. By the way, what are the 4 possibilities that we can have if it's 50-50? We can have a girl. We can have a boy. We can have a boy and a girl. And then what? A girl and then a boy. You guys okay with those? That's the only 4 outcomes we can have? Okay. Before I go any farther, in your groups, I want you to tell me, are these 2 probabilities asking for the same thing or not? And if they're different, what's different about them? So I'll read them both to you and then I want you to talk about it. Find the probability of obtaining a family with 2 girls, given that the family has at least 1 girl. And the second one is, find the probability of obtaining a family with 2 girls, given that the older sibling is a girl. Okay? Those are your 2 statistical statements. I want you to tell me, are they the same, are they different? And if they're different, how are they different? All right. How many groups at least acknowledge these are conditional probabilities? Mr. Wood, I got it. You said the word given in there. You ordered it differently on those. Well, not really, but I at least recognize that I've been given different conditions on problems 1 and 2. And if I've been given different conditions, I'm not going to have the same probability, but I might. So let's find the probability of obtaining a family of 2 girls given that the family has 1 girl. So I'm going to write that as probability of 2 girls given 1 girl. How many groups agreed that that was the first question was asking that? Okay. How about the second question? Find the probability of obtaining 2 girls. Well, that's asking me the same probability. 2 girls, given that what? What's different in number 2? Older girl. So I'm just going to write an arrow up That's official studies right there. It means the older one's a girl. Are you okay with that condition? Do we see that those conditions are different? Hey, we still find it as a conditional probability. It is going to be success over total. It's going to be the intersection divided by just the probability of the one girl. So in this case, let's look at solving problem number 1. I need the probability of 2 girls given that there's 1 girl. That's what I'm looking for. I need the probability of having 2 girls if there's 1 girl. Does that make sense? Because that intersection right here, and that's kind of confusing for students. 2 girls and 1 girl. Mr. Wood, I don't quite get that. Here's the deal. Think differently about your Venn diagram. 2 girls exists within a subset of 1 girl. Okay? It's not an overlapping type thing in this situation. 2 girls is right here. Does that make sense? And you've got girl-boy and boy-girl. In that diagram now, does that represent kind of what's happening? The intersection is where they overlap. Everything of girl-girl is in the group of at least 1 girl. So in this case, the intersection of 2 girls and 1 girl is just right here. And that's 1. There's only 1 place where that happens when you get girl-girl. Divided by, well, how many ways are there to have at least 1 girl?
3.
3. 1, 2, and 3. The probability is 1/3. Again, one way to see it in terms of a condition. How many ways are there to get 2 girls if you have 1 girl? Well, there's 1, 2, 3 ways for me to have 1 girl. Out of 3 ways for me to have 1 girl, only 1 way, 1 out of 3, can I get 2 girls when I have a girl. Does that make sense? So that probably is 1/3, which is like 0.333, never ending. Number 2, find the probability of obtaining a family with 2 girls, given that the older sibling is a girl. Hopefully you'll agree there's only 1 way to get 2 girls. That's a girl and a girl. So that's going to be 1. How many ways do we have that the older sibling's a girl? 2. You guys agree with that? So this probability is 1/2. 1/2. There's only 1 way that you can get, what's that?
Because you can have an older girl and a younger boy, and you can have an older girl and a younger
This,
boy.
let's call this first column the oldest kid, and that one's my youngest kid. The condition here is that the oldest one is a girl. That's the oldest one being a girl. That's the oldest one being a girl. I can't count this. Right? Out of my set of first one being a girl, that's my denominator too. How many ways are there for me to get girl, girl? There's just 1 way out of 2. That's why it's 1/2. All right. Last little bit here. I'm not going to do that. I want to do this one. All right. Of the horror movies reviewed by Katie and Kira on their television show, Katie gave thumbs up to 25. Kira gave this rating to 40. And 15 were rated thumbs up by both Katie and Kira. Those are my daughter's names, by the way. Suppose that one of these 100 movies is randomly selected. Here's how geeky we are. My wife's name's Chandra. Starts with the letter C. My name's Corey. Starts with the letter C. She teaches math. I teach math. So our daughter's name is Cadence, so we call her Katie. We had to spell Kira with a C because we like the name Kira. And so when you put all of our names together, we have C to the 4, C4. And then the ending Katie, Corey, the ending Chandra, Kira. So we match the endings. And now the other thing I'll tell you about kids' names. When you're a teacher and you're married to a teacher, there's a lot of names you don't want to name your kids. I'll leave it at that. Because there, I remember we were coming up with naming our kids, and I'd be like, well, what about this name? I like this name. She's like, no. And then she's like, well, I really like this name. I'm like, So, anyway, we're watching Disney shows here, apparently. What I want you guys to do right now, before I answer these questions, or we answer these questions, construct a Venn diagram that represents this data correctly. Okay? So make a Venn diagram. Get the numbers in the right locations. Your intersection, 15 was thumbs up by Katie, and 15 Katie and Kira both. So that should be your intersection right there. So we're working off. The left-hand side, I'm going to choose to make that one Katie, and the other one I'm going to make Kira. Katie gave, she's much more discerning in her thumb uppiness. She only gave thumbs up to 25 of the 100 movies. However, she's given 15 of them with Kira. So my question is, and this is the key mistake area, most students have 25 written right there. Can't be. Has to be 10. And as I said, the issue that students have is setting up the diagram. The probability stuff's easy. All right? Using the same logic for Kira, she liked 40, 15 of them they shared, so what is that, 25 that she did alone? Is that right? Okay. How many movies did they both not like?
15.
Those on the outside.
Wait, did they both not like?
Did they both not like? How many movies did they watch? How many movies did they both not like? 50. It should match with your data. How many people got that Venn diagram correct? Not a lot of hands here. How many people in the future can get that Venn diagram correct? Because I'll tell you, the answering of the questions is easy if you have the diagram correct. So, given the movie was rated thumbs up by Katie, what's the probability it also received this rating from Kira? Conditional probability here. You guys go ahead and calculate it. There's 100 movies that they watched over.
Yeah.
Given the movie was rated thumbs up by Katie, what's the probability to also receive that rating from Kira? So, writing the condition, that's the hard part. Remember, conditions given, that will come second. So, probability that, I'm going to say thumbs up Kira and thumbs up Katie, given Katie thumbs up. Well, movies that Katie gave thumbs up to. Katie gave thumbs up to a total of 25 movies. Of those 25 movies that Katie gave a thumbs up to, how many did Kira also give a thumbs up to? Should be 15. So 15 over 25, 0.6. How many people actually came up with 0.6 there? Here's what happens with probability. As we continue to work probability, which we're going to do next week, it becomes a game to see. Because every time you're like, I think I have the answer, but I don't know. And then I'm going to start providing you answers, and you're going to get the answer that matches. You're like, sweet, I got it. Because it's like gambling every time. Second one. If the movie did not receive thumbs up from Katie, what is the probability that it also did not receive the thumbs up from Kira? So we're looking at knots and knots again. Agreed?
It's the other way around.
It's flip-flop the other way around? I'd rather do this one. This one's harder. Katie. Her name's Katie, so we just call it Katie. Her name's Cadence, so we call her Cadence. We just spell it funky. Well, her official name is Cadence. C-A-D-E-N-C. All right. No thumbs up from Katie. How many movies were no thumbs up from Katie? 75. The 25 that Kira did by herself and the 50 that they both didn't do. So there's 75 movies that Katie thumbed down. Of the, or given the condition that she thumbed down 75, what is the probability that Kira also thumbed down the movie? Or they both do? Hopefully you're saying that's 50. That's where they both thumb down. Or not thumb up and not thumb up. Compliments there. So it should be 50 over 75 for that one. Which is 0.667. Not thumbs up from Katie. Those two. Does that make sense? What's that? The intersection. If you want to see the math that goes with it, it's the intersect up top. I'm just going to write thumbs down from Katie and thumbs down from Kira. That's up top. Divided by thumbs down from Katie. That's our conditional probability. The 75 is not thumbs up from Katie. It's complement of Katie thumbs up. It's Katie thumbs up. I'm just going to write Katie thumbs up was 25. It was given originally.
No, because you're adding the one that they did together.
Does that match now? Are you okay? It's the math, the calculator plug-in is the easy part. The hard part is figuring out if it's 50 over 75. That 25 represents just Kira giving us thumb up and Katie not. All right. Are we starting to see what I'm talking about when probability is sometimes easy, sometimes hard? Okay? The calculation is not so bad. We've got about 5 more minutes here. I want to start independence. I already talked about independence yesterday a little bit. I said if the events are independent, you can multiply. This is a, put on your geometry cap.
Oh gosh, what's that?
This is an if and only if statement. Especially the way it started.
Oh, okay, no. Andrea, she just drew this little girl right for a second. She was fucking past the She still teaches. Yeah, she still teaches, and her breath still sings. Like,
All right. This is an if and only if statement. If it's given to you that the events A and B are independent, then the probability of A times the probability of B equals the probability of A and B. And that's, they're going to say, you're going to see it in wordings. If A and B are given that A and B are independent, what's their intersection? Or what's, a very simple example of independent events means they kind of don't impact each other. For example, event A, I will call flipping the coin heads or tails. Event B, I'll call rolling the dice. Okay? So, hopefully you'll agree in terms of independence, the outcome of flipping the coin does not impact the outcome of me rolling that dice. Does that make sense in terms of independence? Right? So when we have independent events, you can multiply probabilities together. For example, if I asked you the question, what is the probability that I flip the coin and then roll a 3? Flip the coin and get a head. I should actually give you a condition there. Flip the coin, I don't know, 100% this one. What's the probability that I flip a coin and get a head and then roll a dice and roll a 3? Hopefully you know that getting a head is 1/2. And rolling the 3 is 1/6. That means my theoretical probability, since these two events are independent, would be 1/2 times 1/6 or 1/12. Okay? You guys have actually kind of done that, and we did a little bit of it yesterday. What we're going to talk about on Monday is how we're going to test for independence. And the test for independence will really come back to our conditional probabilities. Okay? So we're going to blend independence with conditions on Monday. For now, I think I'm going to skip this because, oh dear God, you've seen it on every CST that you've had, which are finally going away, by the way. Now that you guys are seniors, CSTs are gone.
Now we can do it.
Right. So, are you guys okay that I don't have to go over this? 8 red marbles, 10 blue, 15. What's the probability that they? Yes? Do we need to do these? Okay. It hurts. Okay, that's what's sad. It's
I think it was
sad.
after my concussion, so it's okay.
Okay. But the only thing. Oh wait. The only thing I want to talk about real quick is the idea of replacement versus non-replacement. Because the probabilities change if you put the marble back in the bag versus if you don't put the marble back in the bag. I'm only going to list first one, probably picking 4 green marbles in a row if you don't return the marbles. Well, if you don't return the marbles, we're talking about green marbles. Hopefully you're going to say it's 15 over whatever that total is. I don't know what it is, 18 and 15, 33? Okay? Okay? You don't put them back. That means there is now 14 green marbles out of 32. You don't put that one back. There's 13 green marbles out of 31. Then there's 12 green marbles out of 30. Those events, we would multiply them together, reaching into the bag, then reaching into the bag, then reaching into the bag, then reaching into the bag. Again, non-replacement means I reached into the bag, I pulled out a green marble, and I set it down. Okay? The difference. If you put the marble back in the bag, it should make sense to you. That would be 15 out of 33 times 15 out of 33 times 15 out of 33 times 15 out of 33. Yeah? That's the easy stuff there. I don't even want to, I need to take it out of the notes. This is where we will pick up. This is where we will pick up on Monday. So independence. You print out your notes up for independence. We will be here. And let's go with, at this point, Chapter 6 work you should have done. I will post it right now.